Hi. Today's tutorial will be based on Unet architecture as well, the same as the previous one. We will do melanoma classification. Basically, it will be based on Unet architecture and using Python and TensorFlow. We will download a dataset and we will try to predict a mask that classify the position of the melanoma inside our images. So let's start. First of all, let's cover the Unet architecture. Okay, let's dive into a Unet architecture. A Unet architecture is a type of deep neural networks that commonly used for image segmentation tasks. And image segmentation is a process of diving an image into different parts and assigning a label to each detected part. This is useful in various applications like medical image analysis, where you might want to identify and classify different structures within an image, such as organs and tumor. As you can see, this is a U shape. The Unet architecture gets its name from its shape, which looks like U when visualize it as a diagram. As you can see, it consists of two parts. There is the left part and there is the right part. Encoder is the part on the left side of the U shape. It takes the input image and gradually reduces its spatial dimensions while capturing important features. This helps the network learn high-level representations of the input image. The encoder follows a typical architecture of convolutional networks. As you can see, this is, for example, has 64 filters, and this one has 128, and this one 256. Basically, it consists of repeated applications of two 3x3 convolutions, each followed by a rectified linear unit, a ReLU, and a 2x2 max pooling. For example, this red cross, a 2x2 max pooling operation with a stride 2 for the down sampling. The decoder, this part is on the right side of the U shape. It takes the feature learned by the encoder and gradually increase the spatial dimensions back to the original size of the input image. The decoder's job is to generate segmentation map that assigns a label to each pixel, indicating which part of the image it belongs to. So the key feature of the Unet architecture is its use of skip connections. You can see here, for example, is the skip connections. These connections allow information from the encoder to directly reach corresponding layer in the decoder. This helps the network combine both high-level and low-level features, which can lead to more accuracy in the segmentation results. Okay, let's start coding, and of course, before we will start the coding process, we will have to download our dataset. So let's open a browser and let's search for Isaac Challenge database. Of course, I will leave a link for that, and you can see we have to download all the columns, the training data, the ground truth, the validation, and the test data. It's about 6 files. I already downloaded and put it on my local folder. As you can see, I'm browsing the images on the training folder, and these are the ground truth of the training. That means that someone has marked the melanoma location. So now we can see, we can compare one of the images, the original image and the mask image. So let's start coding. First of all, let's dive into the data and understand our data. We have to see what is inside, what is, for example, the mask, what it contains. As promised, I will leave in the code a link for the dataset so you can download locally. let's start with importing some Python libraries. The major one, of course, would be OpenCV, NumPy, and TensorFlow. And let's start with a height of 128 and a width of 128. That means that all the images will be resized to this width and height. So this is the path for the images. And let's build also a path for the training data. That means the images and the masks. Please notice that the images are JPEG images and the masks are PNG images. So you just have to notice it and load the relevant extension. Let's see how many images we have on the train folders. It should be identical. Okay, let's get the list of the images and the list of the mask. And let's print the length of those two arrays. Okay, so we have basically about 2,500 images. We will do some data augmentation in order to enlarge our dataset. I will explain it later, since 2,000 images is and not much images for the training process. So let's load one of the images and one of the mask and display it just to see that everything is okay. I'm using a straightforward OpenCV functions. Let's resize it since the image is a little big. So we resize it to our required dimensions. Let's also load the mask. Please notice that I'm loading it as a grayscale, so it would be only one channel and not three channels. And let's show both images. Let's run it. As you can see, we have both images, the training images and the relevant mask. Okay, let's continue to the next step. Now we would like to do some data augmentation. What does it mean? We will take an image and we create a similar image by doing some manipulation. We will do three manipulations. The one would be horizontal flip, the second one will be vertical flip, and the last one will be a little rotation. That means that every image will be so for every image we have 4 copies, the original one and the 3 manipulations. So basically, if we have 2,500, we can create with this process about 10,000 of images. So the first step will be the horizontal flip. Second one will be the vertical flip. Of course, all the code will be in my GitHub, so you can use it free. And the last one will be rotation. The values are the let's say, the angle of the rotation. So we will do a little twist of the image. You will show it. I will show it in a few seconds. So now let's display those three manipulation, augmentation. Okay, so now we have 4 images and 1 mask. As you can see, there is a horizontal flip, vertical flip, and a little bit of rotation. That gives us more images for the training process. Now let's see the mask. What is inside the mask? In order to see it, we will shrink the mask to 16 by 16, and let's print the value of the mask. It's very interesting to see what is inside the mask. So we print in this mask 16 variable. Let's run it. As you can see, the 0 is the background, the 255 is the object, and we have more values. For example, 64, 17. We have to change the values to binary values. That means that to 0 and 1, or maybe 0 and 255 if we are speaking about an image. So all the background will be 0, and the object, which is the melanoma, will be 255. So in order to achieve that, we will change the values for the mask, for the all mask. Let's try it on our first mask. So all the values above 0 will be the value of 1, and all the values, all the rest will be 0. This will help us with the training process. That means that the value, wait a second, I have to fix the code. Yes, it should be mask 16. Yes, let's continue. I'm doing a freestyle, as you can see, so there may be a syntax error, but now you can see this is the original mask and this is the mask for the training. The 1 is the object and the 0 is the background. Good. So now we are ready to run for the all images and create 2 types of array that will be transformed to a NumPy array, but basically we'll create 2. One will be for the images, the training images, and one will be for the mask. So first of all, let's deal with the train images. Each of the images will be transformed to our required size for the model, and the mask will be transformed for our required 0 and 1 values. So we will run a for loop for all the files, all the training files and all the masks. As you can see, this for loop is running through all the list of images and all the list of masks. These are of course the training data. And we will show the process using the TQDM Python library, so we can see the steps inside the for loop. Okay, let's start. First of all, let's load each of the images using the IMRead, the OpenCV library. It would be, of course, a color image. Next, we will resize it to our required dimensions, 120 by 128. Then we'll divide the value by 255, so the values of the images would be between 0 and 1. And then we will convert it to float 32. It will reduce the time for the training, since before it would be float 64. Then we'll append each image to our all images lists. Then we will load the mask. The mask is of course a grayscale. We will resize it to 128 by 128, same of our original image. Then we will do the transformation as I mentioned before. All the values of the mask that are above 0 would be 1, and all the rest of course will stay 0. And we are adding this mask to our mask images array. Now we are creating the data augmentation for each of those images. We will do an horizontal flip, a vertical flip, and rotation as I explained it earlier. So let's wait a few more minutes to display the code. Please notice that I'm creating not only an augmentation process, an augmented image for the original image, but also for the mask. So also the mask is being transformed to horizontal, vertical, and a rotation. So basically the number of training images for the original images and the mask are the same. Should be the same, about 10,000 of images and masks. And each of those augmented images mask is also inserted to the parallel list, the all images list or the mask images list. So this is I believe this is the second one, and we are close to the final one, the rotation process. The last step is converting the list to a numpy array. So we will use the array function. So basically we are creating an images numpy array and masks numpy array. Both of course are the training images and masks. Let's also double check that the type of the mask is integer, because basically the values should be 0 and 1. And at last, let's print the shapes of those two numpy arrays, and we will see how many images and how many masks we have in the last phase. So let's run it. Okay, we can close all the images. We have an syntax error. Oh, okay, the resize. It should be the mask, not the image mask. Let's replace it and run it again. I have another error in the flip, in the horizontal flip. Let's check it. Oh, the function is wrong. I forgot to create a variable, an object variable, and also the function is wrong. Okay, now it's okay. Let's run it again. Okay, now it's running through all the 2,500 images. Let's fast forward the process. It's about 10 minutes, so let's run directly to the last steps. As you can see, now we have about 10,000 images. Each one of them is about 128 by 128. Okay, the next step would be running the same process on the test images. So we would like to create NumPy array based on the test data. So let's see the name of the folders. Basically, it will be the same process for the training, but we have to double check the variables names and the folders names. So let's copy the folder name for the train images and the relevant folder name for the mask images, and let's also copy paste the loop through those images. Let's see, we have to create a similar lists for the test images and the test masks. Let's call it all test images and mask test images, and let's change the name of the variable during the for loop process. We also have to change the name of the NumPy array, the one for the images and one for the masks. I also have a bug here that I will fix later, but it's a good opportunity for you to see if you find it now. So after we finish creating the training dataset and the test dataset, we would like to store it and save it locally as a NumPy array object. So we will write 4 commands for each of our NumPy arrays. So we are done. Let's run the full process. We're expecting to see 4 files, 2 for the training and 2 for the tests. Once again, we are running to a fast forward and let's see the result. Okay, as expected, we have 4 files, 2 for the train and 2 for the test. Okay, now we are ready to build our Unet model. Let's create a new Python file. Basically, this process was covered in my 2 or 3 previous Unet tutorials, so I will do only a brief on this process. We are loading the TensorFlow relevant layers, and we will also load the model object. And a Unet model is based on convolutional blocks. We have 1, 2, 3, 4 blocks on the decoder side and 4 blocks on the encoder side, and we have one bridge. So let's create a function for the convolutional block. Each of these blocks is based on 2 layers. So this is the first one, the conv 2D, and it's also contain a regulation based on batch normalization, and the activation function is relu. And this is the second, this is the first one, and now this is the second layer. Let's create the second layer. As I said, we have 4 blocks. Each block has 2 layers. So this is the second one. Okay, now let's build another function. We will call it build a model, and we will call this function later on the training process. And in this function, we will build our 4 building blocks, and in each of those building blocks we have a number of neurons. So the first block would have 64 neurons, the second one 128, 256, okay, 256, and 512. The build function takes one argument, the shape, which represents the input shape of the data, and then we are creating the encoder and the bridge and the decoder as well. What is the encoder? The model begins with an input layer, and we iterate through a list of number of filters, progressively increasing the number of filters in each convolution block. For each filter count, we apply the conv block function, which include 2 convolutional layers I mentioned before, batch normalization and relu activation. We also track the intermediate result in the skip_x list, and downsample the feature maps using the max pooling layers. So the bridge is, after the encoding process, we have a bottleneck layer, also known as the bridge. Here we apply another convolution layer with 1024 filters to capture high-level features. The decoder, in this section, we reverse the order of the filter count and feature maps by reversing the num-filter list and skip_x list. We then upsample the feature maps using upsampling 2D layers and concatenate them into a corresponding feature maps from encoder using the concatenate layer. We apply conv block function to each concatenated feature map to decode and refine the segmentation information. And last, the output layer. Finally, we have an output layer that consists of one-on-one convolutional layer followed by a segment activation function. And this layer outputs the binary segmentation mask, where each pixel is assigned a value between 0 and 1, representing the likelihood of belonging to the positive class, which is it melanoma or not melanoma. Okay, the next step, the third one, is creating the model plus training the model. That means we would like to load the data and train the data using the Unet model. So first of all, let's load our saved NumPy arrays, and let's print the shapes of those arrays. Let's print the shape of those 4 numpy arrays and let's run it. It's just an indication that everything okay. As you can see, the last one is not okay. The number of samples, the number of test masks is not equal to the number of images mask. Remember the bug on the first phase of creating the data? As you can see, we have to fix it and run it again. So we have to change this values, this variable was wrong, and let's run it again. And once again, let's fast forward the process, stall the updated numpy array, and let's go back to the training and run the loading again after fixing the previous bug. As now you can see, the data is the same. We have 4,000 images for the test and for the mask as well. So let's continue with building the model. Let's import TensorFlow, and most important, let's import our function that we wrote earlier on step number 2, and we will import the build model function from the code, from the Python code step number 2 model. Let's also import a free relevant functions for the training. I explained later. Let's define a learning rate of 0.001. The best size would be 8 images, and let's run it through 50 epochs. Now we are creating our model, and let's print the summary just to double check that the model was loaded or basically created with no problem. Let's run it. As you can see, we have an error. I think the name of the function is wrong. It's an uppercase and lowercase. Let's go back to step number 2 and let's fix it. It should be with an uppercase S, and let's run it again. Go back to the step number 3, and run it again. Now, as you can see, when we run the summary of the model, it seems okay. So let's define an optimizer. It will be based on Adam with the relevant learning rate, and let's combine our model. The loss function would be binary cross-entropy, since it's a binary classification, a 0 or 1. And let's define our optimizer, and the metrics would be accuracy. Now let's define the number of steps per epoch. Basically, it will be the number of the samples, the number of trained images divided by the batch size, and let's round the result. You will use the numpy ceil function, and that would be the steps per epoch. Let's do the same for the validation steps. That would be for the test data. So we will change the number of test data instead of trained data for this step. Now let's define a file name for the model. We will name it Melanoma Unet.h5. Okay, next we will create a callbacks. Callbacks are special functions in Keras that can call during training, and these callbacks can help in monitoring and optimizing the training process. That means we can change some values during the training process. The model checkpoint is used to save the model weights during the training. The reduced on plateau callbacks is a second callback that is used to dynamically adjust the learning rate during the training. And the last one, the early stopping, and this helps us to prevent overfitting by monitoring a specific metrics, in this case the validation accuracy. And basically that means that if the process would not improve after 20 consecutive epochs, the training will be stopped early. That means it will stop before the total 50 epochs. And now this is the Feit function. We are sending all the relevant arguments, the train images, the train mask, the size of the batch size, and the number of epochs, and also the test data. Our steps per epochs are our validation steps and the callbacks functions. And let's also add a shuffle true in order to shuffle all the training data. And I believe we are ready to run it. Yes. Okay, so basically it's going to run 50 epochs, and the early stopping may stop it earlier. But as for now, we will give the model all the time it needs to run the whole process, but we will jump directly to the last step. As you can see, it took about 2 hours. So let's go to the final process. Okay, now it's done. As you can see, it's run about 22 epochs, and the validation accuracy is about 0.7273. So I believe we are ready to test our model on a fresh image. So let's create a fourth Python file. We will call it test the model, and in this process we would import our saved model, and then we will load a fresh new image from the validation dataset in our local drive and try to predict its masks. So let's load the model. We will use the load underscore model function, and let's print the model summary. This is an indication that the model was loaded with no errors. Okay, as you can see, we have a summary of the model. Let's continue. Let's define the same height and the same width. And next, let's once again browse our data. Let's go to the validation folder, and let's choose one of those images, an image that the model never has seen it before. Let's get the full path for the image. And let's load the image and display it using the OpenCV functions. Okay, let's run it. Okay, the dimension of the image are very big. We probably in the next phase will resize it to a smaller one just to display it. So we will use our required dimension. So let's create another variable. We call it image2, which in this process we will pre-process our image for the model. So we will use the expand dims to create a batch of images. Of course, we have only one image and the batch has 8 images, but just for now we would like to see that we are creating batch of images. As you can see, this is the 1 on 128 by 128. That means that we have a batch of images that contain only one image inside it. It's very important because our model is expecting a batch of images. So now we can run the prediction, and let's print the outcome, which is probably would be our predicted mask. So let's print the shape of the outcome. As you can see, the shape is 128 by 128 by 1. So this is a shape of an image. But it's very important, the values are not 0 or 1. They can be any values between 0 and 1. So since it's a binary classification, we can assume that all the values above 0.5 would be changed to 255. That means that we will change it to a white color, and all the values under 0.5, so these are the predicted value, would be changed to 0. So basically this image would contain 0 values or 255 values. So it would be white or black. So then when we will display the result, we are expecting to see a mask of white and black. Next, let's rescale the result and the image that they can be displayed in one screen. It's only for convenience. So we are reducing by 25%. And this is the resize function in order to get the effect of resize by 25%. This process is on the original image, and now we are doing the resize by 25% on the mask image, our predicted mask image. And what's next? Let's also load the true mask file. That means let's go to our dataset and look for our mask, the real one, and let's display all these 3 images one next to each other. That means the original image, the original mask, and the predicted mask. Let's load it as well, and we will display these 3 images. Let's resize the true mask image to the same size, and now we are ready to display all the 3 images. This is the predicted mask. We name it mask, and the last one should be the true mask, the real mask. Let's run it. As you can see, we have 3 images. Let's arrange it one next to each other. In the middle we have the original image, on the right side the predicted mask, and on the left side the real mask. I hope you enjoyed this tutorial. I hope I am giving you some values using the Unet architecture. Hope to see you on my next tutorial. You are most welcome to subscribe. Bye bye.